the end of class, so you can remind me if there's 10 minutes before the end of class. Feel free to interrupt me if I don't catch it. And we'll hand back the exams then. And not a whole lot to really go through on the exam. A couple things. Most people did really well. The average was really high. I think the average was 85, as I recall, something like that. So as I mentioned on the exam, if you got below 80, take that as a sign that something needs to change. So if you got below 80 on the exam, you need to make some sort of change how you're approaching this, because that didn't work. It was a really easy exam, probably the easiest I've given. And if past history is any indication, the next couple exams are significantly harder. So the average on the next, this exam has always been the highest of the class, and the next two is always significantly harder. I'm just trying to make sure to give you a heads up. I don't want anyone to get a false sense of security because of the first exam and then have any sort of disaster happen later. So keep that in mind. I don't intentionally make them harder. It just seems that that material is a little bit tougher to grasp the first time you hear it. So there's that. Don't get cocky if you did well, and also if you didn't do well, think about what changes can you make to recover. On the exam itself, there wasn't really any I guess there's just a couple comments I had. One thing that surprised me was the first question when I asked about central limit theorem. And so a response that I got a lot was that if we take a lot of data, those individual data points become normally distributed. That's not true. The individual data points are from the same distribution they were if you took 5 of them or if you took 150 of them. But the average, when you take those individual data points and average them together, then the averages are normally distributed. Okay, that's really key. So the other part of that was a lot of people wrote this, which was fine, but I have a feeling just based on this first response that if I would have pressed students to tell me what this means in words, I would have gotten a lot of other strange responses. So make sure you actually understand what this is and can express it in words, so you really get the concept and not just, oh, I know there's this equation, okay? Because it's really important to get these two concepts. And then lastly, just as an exam writing tip, I don't require you to write incomplete sentences, but many times people lost points because they wrote vague phrases that I couldn't decipher when they said, assume normal distribution. Well, I don't know, are you assuming the mean is normal? Are you assuming the individual data points are normal? Lots of examples like that where what you wrote was imprecise, and so I would say writing in a complete sentence will help that. Many times the subject of the sentence was missing and I didn't know what you really meant. So keep that in mind. I don't want you to write a ton of stuff, but be very precise and exact in what you mean when you write a conclusion, say. And that was probably the only other thing worth mentioning is several times, this happens every year, you go through, you do the statistical test correctly, but then you draw the exact opposite conclusion of what you should. So make sure you know, obviously that's a really important thing, to be able to calculate the statistics right, but then to make sure you've got the right conclusion from that. So I'll hand back the exams later, and I'll post the solutions on Blackboard. But this is where we're at now. Hypothesis testing, and we have, these are the steps in hypothesis testing. We've gone over many, many times, and the only variation is in this compare. We can do the fixed level testing, where we compare T and Z with T star and Z star, or we base those hurdle values on area and use P and alpha. So now we're going through all the variations that we went through in Chapter 5. So next one up, excuse me, is when you can assume equal variance, which means that you've taken two data sets and the source of error in those data sets is the same for both. So you have the same equipment, kind of like on the exam, the same equipment that is the major source of error in data set A and the major source of error in data set B. In that case, you would assume those are equal variances and you should pull them together. The reason for that is you get more degrees of freedom when you can say that. Right? You have more information about your system that generally correlates to more degrees of freedom and therefore a more precise test. Everything else is the same. So let's work through this. Let me see, do I have a group problem after this? Let's do this as a group problem. So let's see if we can do this fairly quickly. Obviously, I've got a figure there that probably has something to do with the answer of this problem. The grader didn't know how to grade that because there were calculations. Was that a question? Yes. That looks a lot better. Thanks. Sometimes the projector doesn't project all the images. It's a technical glitch. There are some principles. I've mentioned this if you had a class from me. We've talked about how St. Augustine lays down those rules of interpreting Scripture, that if it seems like there's something wrong in Scripture, there's various understandings, and one of them is a problem with your interpretation. We have a very similar thing here, that if it appears that I make a mistake, there's usually some problem on your end with perceiving it, or there's a technical problem. So we just start with that basic assumption and then explain the data from there. So that's all. Follow those interpretive rules in this class. Anybody have any questions? Pardon? Oh, here we're assuming the variances are equal, so we're going to pool them together. Yep. So this is equal variances, so we need to remember that SP squared. And you can just remember it in words. It's a weighted average of variances. So remembering just that short phrase should allow you to write the equation. All right, let's go over this then. First step, okay, we got our hypotheses down, talked about those a little bit. Second step, assume H0 is true. That sets this distribution. So keep in mind, before we were working with the distribution, that was the distribution of an average. This is the distribution of a difference between two averages. Right? So right here, what am I going to put here? Remember, this is what we always put for the standard deviation. So if this distribution is the distribution of a difference between two means, what am I going to use for the noise in that? Is it SP? What is SP in words? Pardon? Right, it's the weighted average of variances, but variances of what? Variances of the difference between two means? Similar variances, but variances of what? SP squared is the variance of what? Individual measurements, right? Of the data points. But this isn't the distribution of individual points, right? It's a difference between two means. So we need the noise associated with the difference between two means. In this case, what is that going to be? So we need S of y bar minus x bar, or mu y minus mu x. It's going to have something to do with SP, but it's not just this. If it was a mean, what would it be? If this was the distribution of just y bar, what would this be? Good. S divided by the square root of ny. But when we think of a random variable that's the difference between two means, remember if we said W was y minus x, so mu W was mu y minus mu x. Sigma squared of W was this, 1 squared y, sigma squared x. Remember that? And these are averages. So that would be the next step here corresponds to this. Does that make sense? Said another way, we want to calculate a statistic that's going to test this null hypothesis. It's t. The signal is y bar minus x bar. 3.16 minus the hypothesized difference, which is 0. And then the noise in this guy is right there. Does that make sense? Remember, in your t, it's a signal-to-noise ratio, but this signal isn't an individual data point. It's not one mean. That is a difference between two means. So that means that noise has to be what we would build up as the difference between two means. So this is what? Was this 5? And this is 7. Then we need SP. So we have two estimates of the standard deviation. We think about this. We're saying, if we assume the variances are equal, we're saying we have two estimates of the noise, this one, and they both are estimates of the same noise. So let's pull them together and get one estimate of the noise. And we believe this one more than this one, because why? Right, more data points weight in this one. So our weighting factor is degrees of freedom. So we have 4.042 squared plus 6.048 squared. It's easy to forget this squared here. It's easy to forget the other squareds as well. So I saw that a lot. And 10 total. So the variance was 0.002088. So SP, it's also easy to forget to take the square root of it before we use it in our calculation. So we'll put that in there. All right, I'll write this down one more time. Was it 6? No, 5. Thanks. 5 and 7. So T is 2.990. That's pretty far, right? Degrees of freedom. How many degrees of freedom do we have? 10. When you're determining degrees of freedom, the general concept is how many degrees of freedom went into our estimation of the noise. So we're going to do other things, and I think it will behoove you to drill down and always think how many degrees of freedom went into our best estimate of that base level of noise of individual measurements. So we have 10 degrees of freedom there. So we've got a number. We think that's far from the middle. We think it's probably in the tails, which means we're probably going to reject H naught, but we need to actually do the comparison. And we can compare by areas. We can take this guy and get an area, which is a p-value, compare that with alpha, or we could start with alpha and get a t star and compare those two things. So either way works. So I got a p-value of, well, it was less than 0.02 when I looked it up. Can we get that? Was it a one-sided or a two-sided test? Right, two-sided. Because of that, it's two-sided, which means really big values or really small values of the difference between two means will argue against our null hypothesis. Whoops. So there was our t, and the p-value was in between there, and we had to double them. So it's somewhere between 0.02 and 0.01. So our conclusion is we reject the null hypothesis, right? Accept the alternative. So to that, we answer yes. We can conclude that they're different, and we can look and say y is bigger. Any questions on that? All right. So that was one more time through our process. It should be getting routine by now. So we'll just continue with the variations on this theme. Next variation is when we have paired data. So again, just like before, we designed the experiment to eliminate some source of noise, right? So we're trying to block out some source of variation. And to do that, we are pairing our data. We're going to take some physical thing, usually, and we're going to do 2 tests on each thing. And we're going to try to eliminate some source of variation by doing that. So instead of x bar minus y bar, we're going to be looking at the differences and treating it as one data set, a set of differences. All the same thing applies. So, all right, so take a look at this. Start working on this one as a group. So with people around you, and think about answering that question, why did they design the experiment this way? Why did they take the trouble to use the same truck at the 2 temperatures? Anybody have questions on the group problem? Let me know. Oh, yeah, Chris. Oh, say that again.
We subtract two values of data.
Oh.
Just
Oh, okay. It doesn't matter. You can treat it as an absolute value, or you can say, I always just think of it, is it further out in the tails? And that way you can kind of think through the plus or minusness of it. Yes. So yeah, so it doesn't matter what order you do it in. Does everyone see why they're paired differences? Why those two data sets are not independent? I don't see Austin or Chris. Did I miss him? Austin? I don't see him around. Chris was just here, right? Okay. What about? Okay. Yeah, I knew I saw him initially. I need a better system. Okay, everybody doing this? One thing, please pay attention. I saw this, this is probably one of the most prevalent mistakes I saw in the exam, is that when you're doing differences, I don't care which temperature you subtract from which, but you got to keep it the same every time. A lot of you, so if you take 40 minus 80 here, you have to do 40 minus 80 there. You can't flip it around to make it positive and do 80 minus 40. Otherwise, this number's not going to be right. Everyone see that? So you have to be consistent. If you do 40 degrees minus the 80 degrees, do it for every one of those numbers. So I saw a few examples of that on the last exam. And again, why did they design this experiment this way? What are they trying to do by doing a paired t-test, setting it up? Pardon? Right, right. They are looking at the trucks themselves, right? From truck to truck, there's a lot of variance happening there, a lot of noise. They're trying to eliminate that. Does this test eliminate that noise? Does it eliminate the variance from truck to truck? Yes, it does. Right? By taking the same measurements on each truck and doing the difference, it doesn't matter if it trucks here or trucks there, you still have that same distance. Okay, so that, and what was that new term we used for that? It's an example of what? There's a word for it when we try to eliminate a source of variance by doing something different in our experiment. We try to block out that source of noise. That's right. Morgan, blocking is what it's called. And we are going to do more blocking than just this. The general concept is you have some experiment. You're trying to test these, we'll call them factors. All right, we're trying to figure out these factors are going to impact something we're interested in. We'll call it a response. Here the response is the emissions, NO2 emissions. All right, so we're looking, or just NOx. We're looking at NOx emissions. That's our response. And the factors that we're trying to test are, these are the things we think are going to impact the response. Here we're looking at just one factor, temperature. Along the way, when we do this, set up this experiment, we have things we can think of that might mess things up, things that will inflate the noise. We're trying to get this very clear impact of these factors on the response. We're just trying to remove every other thing that we can think of that's going to mess up this path between factors and response. These are called disturbance variables. Sometimes they're called nuisance variables, same sort of thing. And what we're going to try to do is, how do we get rid of those? So the disturbance variables here was the trucks. That's a source of noise. If we do some thinking, we can design an experiment to get rid of it. There could be all sorts of other nuisance variables that we're going to try to control in this setup. And if we can't control them, we're at least going to try to measure them. And then we can do a different sort of analysis of covariance. We're not going to get into that level. But we're going to try to eliminate disturbance variables. If we can't eliminate them, we are going to try to measure them and try to back out their deleterious effect. Okay, so this strategy is, we're gonna flesh this out real soon. So on with the test. Next step is assume H0 is true. So that puts the distribution mu d equals 0. And this right here is going to be S of d bar. So we're going to calculate the statistic, the signal to noise ratio. We have the signal, 0.03631. I'll write that better. Minus the hypothesized difference divided by the noise in that guy, which is the noise of the individual differences divided by the square root of n, which is 10 in this case. So we get a t-value, 2.713. So we're over there. We need to figure out, go from that to some p-value, and we compare it to our area hurdle rate of alpha. To get a p-value, though, we need degrees of freedom. How many degrees, we ask ourselves, how many degrees of freedom went into our estimation of the noise? So we think of, that's the noise in the individual measurements, SD. How many degrees of freedom went into that? Check. 9, it is 9. When we're doing paired differences, we're treating this like we just have one data set of 10 numbers. So nu equals n minus 1. And so we said before, by doing this experiment, we take a hit on these degrees of freedom. We only have 9 in this test. If we were going to unpair them and do 20 runs, we'd have up to how many? Up to 18 if we could pool the variances. If we can't pool the variances, it'd probably be like 17, maybe 16. Okay, so we're willing to do that in hopes that we've reduced the noise enough where it's still a more sensitive test, even though we're taking a hit on degrees of freedom. So I got a p-value. We can't find 2.713, but let's see. There's 2.262 has a p-value of 0.025. And there's 2.821 has 0.01. And this is what we have. Does everyone, can you find these two in the book? Anyone find those? Yes? No? Okay. Someone nodded their head, yes. Reminded me of a story. I had a cultural moment when I was at UND. One year we had a ton of graduate students who were from India. I mean, it was the whole class, and I was teaching advanced reactor design to like 30 students, and they were all from India, and they all were just over to the US. And I'd ask them a question, say, do you understand that? And they would do this. And I thought they were saying no, but they were smiling. They were real happy with not knowing. They'd kind of go like this. And so then I'd go over again and say, do you get this? And then they would smile and do the same thing to me. And I went over it again. And then finally they told me, Dr. Mugley, when we do this thing, it means yes. And so I realized, like, oh, that makes a lot more sense why you were so happy that you didn't understand this stuff. So anyway, I'm glad you guys just used the traditional up and down motion to tell me that you know these things. Or at least one person did. A lot of you use a non-traditional blank stare with no movement at all. So that isn't working for me so well. Okay, so these are the two p-values, right? But does that mean our p-value is in between these two? Not quite yet. What do we need to do to this? Double it. It's a two-sided test. So we need to double those. So somewhere between 2 and 5%, which means, what do we do? What's our conclusion? So our p-value, and if alpha is 0.05, we compare those to do what? In statistical jargon would be, stare blankly at, yes? Yes, and then in terms of rejecting, accepting, well, reject, I know this is probably so basic you don't want to answer, that's why. We reject H naught, We say no to him, say yes here. We can conclude they're different. So when we go back to the sense, we answer this, yes, they are different. And in fact, we would say, 40 degrees gives higher NOx emissions, greater NOx emissions, than the truck at 80 degrees. Any questions on that? Yeah?
Remind me what you said about if it is exactly 5%.
If it's exactly 5%, don't worry about that too much. That's, in the real world, that 5% is an arbitrary number. And so even in the real world, if it's 4%, 5 or 6%, you're going to be doing the same thing as, I'm going to look at this and weigh what are the costs of being wrong on this, of calling it, of rejecting H0 or not rejecting it, and balance that. So that alpha level is kind of an arbitrary thing that can move. So in this class, we're just going to draw a clear line at 5% and say reject or not. In the real world, you're going to think about it a lot more. Okay? This is a lot more, gives you information on a decision and doesn't lock you into, oh, here's an algorithm and I have to make this decision, right? Okay, on the exam, add up your points. I may have added a number. Oh, wait, what was that? You may have misunderstood my adding of your points, and Blackboard may reflect the wrong score. That's consistent with your misunderstanding. So if that's the case, let me know and I will fix your error. That can happen. So please do that. If you say, okay, I think that maybe that there's too many points taken off or too few, you can come talk to me there, but you got to be prepared to make your case, and I'll listen to it. But how I grade exams, I grade one problem at a time, and my first pass is I look to see who's did it all right, get those out of the way. Then I've got down to the ones who have done it incorrectly, so I can see the common threads. I can try to take off the same amount of points for each common mistake. So I try really hard to make these things as precise, as consistent as possible. But let me know if you have a disagreement, but make your case in that example, in that sort of thing. Okay, we're not done yet, although it may seem like we're done. We're not done. Fixed level testing, we've talked about that. We know what that is. So for fixed level testing, write this down before we go. We're going to think about fixed level testing for quite a while now. So we have some null hypothesis, some alternative hypothesis. We're going to compute a statistic like t, and then what we're going to do is we're going to say, well, alpha is going to give me some t star. I should put in assume H0 is true. So when I assume H0 is true and I draw this distribution, then I'm going to go to my alpha, which is, say, 5%, and I'm going to say, here's a t star. If it's single-sided, it would be like that. If it's two-sided, it would be like that. Right? And so those two areas would be combined for alpha. And what, conceptually, really try to get this, out here in the tails, if we get an x bar, if that's what we're testing, if we get an x bar that gives us a t, in the tails, we reject the null hypothesis. So anything out here, anything out there on the two-sided test, we are going to reject the null hypothesis, right? Let's think about the two ways we can be wrong. The two ways we can be wrong is we reject the null hypothesis when it is true, right? Think about this distribution. If the null hypothesis is true, this distribution is really here, and we got a value in the rejection region simply by random chance, which can happen, and what we would do is we would reject the null hypothesis. If we get a number out here, we say it's very unlikely this thing is true. We'd throw it out, and we made a mistake, right? And that can happen, if alpha is 5%, that happens 5% of the time. That's okay. I think you can get a hold of that. The harder one takes a few more steps is the other mistake we can have. All right, I just said we can reject the null hypothesis when it is true. We can fail to reject the null hypothesis when it is false. So when we unpack that, let's start backwards. When the null hypothesis is false, is it here? No, it's somewhere else, right? We don't know where it is. It's somewhere else. Let's say somewhere over here. Let's say it's right over here. If that's really where, say, X bar is located, when we go get our sample, that sample is going to come from what distribution? Our null hypothesis, that's not right, or this distribution, which is true. Where is X bar going to drop out of? This one or this one? This one, right? Our data, if this is the true one, our data is going to come from here. Does everyone see that? And now think about it. We're testing this black distribution. So if we get a value in the rejection region, we're going to reject the null hypothesis and make the right decision. Right? The null hypothesis, it's not there, it's here. So anytime we get a number out here in the rejection region, we're okay. But sometimes we get a number out here, right? In this case, we would not reject the null hypothesis, even though we should have. What area would correspond to the probability of getting a number in here? Right there. That's right. Remember, the data is coming from the real one, right? So we're going to drop out an X bar from this green distribution, and a certain fraction of the time, it's going to come out over here in this unhappy place where we make a mistake. Yeah?
Wouldn't it be the little tail end of the black data?
No. Where does X bar come from? The black one or the green one? We're testing the black one, but data's coming from the green one, right? So the data comes from this one. If this one is true. Yeah, I know this is the hardest concept in the class. I think by far. It's the hardest concept to get your head around. Once you get it, it's easy, which makes it really hard to teach. So, but I'll try. Okay, so now let's think about what if, all right, we'll think about this last thing. It'll be a Friday cliffhanger, not so much. But try to get this over the weekend and think about if this distribution is really, if the null hypothesis is really untrue, if this green one is really far away, does that make it, are we going to make the decision right more or less than if we're just looking for a small difference? All right, I'm not going to wait for an answer because I'm not sure you heard the question. So we'll talk about it on Monday. Have a good weekend.